discuss the concept of the orthonormal sets, orthogonal sets. So, let us revise what is the orthonormal and orthogonal sets. An orthogonal set M in an inner product space X, X is an inner product space and M is a orthogonal set. An orthogonal set M in an inner product space X is a subset of X in which the elements are pairwise orthogonal. That is, if we take x and y belongs to M, then the inner product of x y will be 0. And a set is said to be orthogonal if it is orthonormal, if it is orthogonal as well as the each element has a norm 1. So, orthogonal means the each pair of the elements satisfy this condition, inner product x y is 0, and orthonormal we mean that it is orthogonal as well as the elements, each element has a norm 1. So, we say the inner product of x y is 0 if x is not equal to y and 1 if x is equal to y. So, such a set is said to be orthonormal set. And if an orthogonal or orthonormal set is countable, then we can arrange in the form of the sequence, and that we call it as a orthonormal or orthogonal sequence respectively. Clear? Now, today we will discuss the concept of total orthonormal sets. The total orthonormal sets is defined as a total set, total orthonormal set, a total set or fundamental set or fundamental set, fundamental set in a norm space X. Norm space X is a subset M of X whose span is dense in X, is dense in X. So, a set is said to be a total set in a norm space X if its span is dense in, it is a subset of X and its span is dense in X. So, we say M is total in X if and only if span of M, closure of the span of M is X. So, that is what they define. Okay. So, M is total in if, and this is obvious from the definition, both if and only parts holds good. Okay. A total orthonormal sets, a total orthonormal family in an inner product space X is called an orthonormal basis for X, is called an orthonormal basis for X. Now, this orthonormal basis is not exactly same as the basis in the sense of the algebra, unless X is finite dimension. In case of the X finite dimension, both orthonormal basis and basis give the same concept. But if X is not finite dimensional, then this will be different concept than the basis of the vector space. Okay. So, in as a remark you can say that if X is finite dimensional vector space, then the orthonormal basis and the basis in usual sense have the same meaning. Okay, have the same sense, but in case of the infinite it will be different, but in general it's not a basis in the sense of algebra, but in general orthonormal orthonormal basis orthonormal basis is not a basis is not a basis in the sense of algebra. This is remark. Now, another important point, remark 1 and 2, just like every vector space which is different from 0 singleton set 0 has a basis, similarly here every Hilbert space H, in every Hilbert space H which is different from the singleton set 0, there exists a total orthonormal set. There exists a total orthonormal. There exists a total orthonormal basis. And this is then total orthonormal basis. Orthonormal basis or total orthonormal set. Total orthonormal set. Total orthonormal set. The proof is simple in case of the finite dimensional. It is clear because the finite dimensional, the orthonormal sequence, orthonormal set, we can have it a corresponding linearly independent set, and span is also we can get it as the entire X. Okay. But for the other Hilbert space which is separable, the proof follows from this our Gram-Smith process. It can Smith process, one can convert it to a linearly independent set and get this thing. And for the general case, the proof is using the Jones lemma for non-separable case. So, we are not going in detail for that. Okay. Then another remark is all total orthonormal sets in a given Hilbert space H, in a given Hilbert space H, in a given Hilbert space H which is different from singleton set 0, have the same cardinality. This cardinality is called the Hilbert dimension or the orthogonal dimension of H. The latter is called have the same cardinality, and this is known as the Hilbert dimension. This cardinality is known as Hilbert dimension or orthogonal dimension of H. Orthogonal dimension of H. Okay. So, these are few things which we can keep. Now, we have we wanted to extend our orthonormal sequence. So, let us take one results which says that the orthonormal set cannot be augmented to a more extensive orthonormal set by simply adding one element. Suppose a set is given which is the orthogonal sets or orthonormal sets, and we wanted to enhance this dimension by adding one more elements, then it will not be possible to add a non-zero element in it. So, that the entire set with a larger dimension will be orthonormal. Okay? It is not possible. So, the theorem exactly says is, let M be a subset of an inner product space X, IPS, inner product space X, then right, if M is total in X, total in X, then there does not exist a non-zero X belonging to capital X which is orthogonal to every element of M. That is, X is orthogonal to M will imply X is 0. So, the meaning is that is, we can say that a total orthonormal set cannot be augmented to a more extensive orthonormal set by the adjunction, by adding new element, by adding of new non-zero elements. That is, if M is a total orthonormal set, then we cannot enhance it to a total orthonormal set having the more element just by introducing one more non-zero element, because as soon as we introduce one non-zero element, then that non-zero element cannot be orthogonal to every element of M. That is the second part of this theorem says, if X is complete, if the inner product, if IPS is complete, that is if X as a Hilbert space is complete, that condition is also, then the X perpendicular to X implies X equal to 0, then this condition, then the condition X orthogonal to M implies X equal to 0, this condition is also sufficient condition X is also sufficient for totality, for the totality LITY double L for a totality of M in X. Okay, let's see the proof of it. So first we want to show that M is total in X, then there does not exist a non-zero X which is orthogonal to every element of this. So suppose M is total and X is belonging to M perpendicular, then we will say X will come out to be 0. Okay. So let us see. Now X is an inner product space. Since X is a inner product space and every inner product space has its completion, we can convert it or we can have a completion of X. So let H be the, and let H be its completion, be the completion of X. Okay. I think I have given the concept of completion. If X be a inner product space, then and H be a Hilbert space, then there exists a W which has a one-to-one correspondence and closure of W is H. Then we say H is the completion of X. So that is the meaning of this. Then X regarded as a subspace of A. So since H is a completion of A, so X is a subspace of H, is a subspace of H, and it is dense in H, and is dense in H. By definition, dense in H, because X is a has a isomorphic with the set W which is subset of H, and W eclogial is H. So we can say, assume that H is also dense in H, X is also dense in. Okay. Now so the span of M is dense in M. Now what is given is M is total in X. This is given, M is total in X. So by definition of the total set, a set is said to be a total or fundamental in a normal space if the closure of the span is M. So that's definition shows that since M is total in this, therefore span of M is densest. So span of M closure is H, is X, hence in H, hence span of M closure is H, because H is the completion of X. Okay. Now there is one lemma which was proved earlier. If not, then we can prove right now. The lemma says, now using this lemma, use the following lemma. What the lemma says, for any subset M which is not empty set of a Hilbert space, H, for any subset M of a Hilbert space H, the span of M is dense in H, if and only if orthogonal complement of M is a singleton set 0. Okay. So this lemma, let it be the lemma say A. Okay. The proof we will see later on, lemma A. We can make use of this lemma, and because of this lemma we say what's the lemma says, a subset M of a Hilbert space H is given, then span of M is dense in H if only if the orthogonal complement of this is 0. Here M is giving total, the span of this H, and H is a Hilbert space. So, this shows that orthogonal complement of M perpendicular is in H is 0. So, using this lemma we have this lemma we have the orthogonal complement of M in H is singleton set 0, and that is if x is an element of capital X and x is orthogonal perpendicular, x is orthogonal to M, then x must be 0. Because of this, any orthogonal complement of H is singleton 0, it means M perpendicular 0. So, if x belongs to X and x is perpendicular to M, so according to this x must be 0. So, what we started is, we have started this that M is total in this, then there exists a non-zero x which is orthogonal to M imply which is orthogonal to every element of M, that is x is there does not exist, means if there exists an x which is orthogonal to M, then x must be 0. So, we have started with an x belonging to M which is orthogonal to M. Now, according to this we have shown that total of this M is total in X, so span of this H, therefore, by this lemma the perpendicular orthogonal complement of M must be singleton set M, therefore, we get x to be 0. So, this proves the one side. Okay. Sufficient part, let us see the sufficient part. For the sufficient part, that is part B, hence A follows. Okay. For B, the proof of B, if X is a Hilbert space, and M satisfy the condition, and M X is a Hilbert X is complete means X is a Hilbert space and M satisfy the condition that is x is orthogonal to M implies x is 0. Okay. X satisfy this condition, so that according to this result, according to the lemma that x M is total in this, so that M perpendicular is singleton 0. So, by lemma A, that is M is total in X, and that proves the results. Okay. So, only thing proving of the lemma. So, let us see the proof of the lemma. Clear? So, this completes the proof. Now, proof of the lemma. Okay. Now, what was the lemma is? The lemma was, okay, for any subset M of a Hilbert space H, the span of M is dense in H if and only if A perpendicular to this. So, statement of the lemma was this. So, this was the, should I write lemma? The lemma was, for any subset okay, for any subset M which is non-zero, non-empty of a Hilbert space H, the span of M density, the span of this closure is H if and only if M orthogonal is singleton set 0. So, proof of this lemma. First is, let us see, let x is perpendicular to this. Let x belongs to M perpendicular. Okay, and then we want to show x to be 0, and we assume V is the span of M to be dense in H. Dense in H. That is the closure of V bar is H. Okay. Now let x belongs to H. So x belongs to the closure of the span M. Therefore, there is a sequence xn in V such that xn will go to x, because x belongs to the span of V M, which is V, span of M, which is V bar. So we can take a sequence xn in V which converges to x by dem. Okay. Now since x belongs to M perpendicular, therefore and M perpendicular is orthogonal to V, because closure of span of V, span of M is V, and M perpendicular, this will be orthogonal to V. Therefore, we have xn inner product xn and x must be 0, because xn is an element of V, x is an element in the x is element of the M perpendicular, x is an element of the M perpendicular, x belongs to, what is this? Let x belongs to H. No, this something. Okay, x belongs to it. It's okay. So x product of this inner product will be 0, but by continuity of this inner product, this will give product. We say xn converges to x implies inner product xn comma x will converge to xx, but this is 0. So this part, which is the norm of x square, should be 0, hence this implies x is 0. Okay. So one way it is clear that if x is an element of M perpendicular and span of M is H, then x must be 0. Okay. So this complete one side. The converse of this, conversely, suppose M perpendicular, orthogonal complement of M is 0. Okay. Now if x is orthogonal to V is the span of M, then x must be orthogonal to M, because V is the span of this. So this implies that x will be the element of M perpendicular orthogonal, but M perpendicular is 0. So this shows that V perpendicular orthogonal complement of B is a singleton set 0. Okay. But any element of H, but H can be expressed as V and V perpendicular by projection theorem. Therefore, the closure of B is H. Therefore, this is 0. Therefore, closure of B is H. Okay. V is a subspace and V closure of H is H, and that proves the results. Okay. So this proves the result. Clear? So lemma is. Now we shall go for this. Now So, this part is okay, completion and is also sufficient. Okay. Now, let us come to the another results, which is giving as totality. Another way also one can define the totality. So, the theorem, okay, an orthonormal set, an orthonormal set M in a Hilbert space H is total in H, is total in H if and only if and only if for all x belongs to H, the Parseval relation holds. Parseval relation holds. That is, what is the Parseval relation is? That is sigma of modulus inner product of E k whole square over k is norm x square, where E k are the sequence of, where E k's are the sequence of the orthonormal sequences, is it not? E k's are orthonormal sequence in that, okay, where E k's are orthonormal sequences in a Hilbert space H, okay, in H. Clear? That's what. So, now this is another way of defining the total set. One way we have introduced the total set H. This is M is total in X if the closure of the span is H. And this is this one fourth. This is third. Orthonormal set. This was the definition of the total set. M is total if the closure of the span is M. And using this thing, we have proved one result, and the result was that if M be a total in X, then there does not exist a non-zero X such that which is orthogonal to every element of M. Okay? And if X is complete, then this is also a sufficient condition. Now, this is another way of defining the total. What is that? Another set, an orthonormal set M in Hilbert space is total in H if and only for all x the Parseval relation holds. Now, this is easy to verify rather than to go for that thing. Okay? Now, let us see the proof of this part. Okay? Proof. Suppose M is not total in H. Suppose M is not total in H. That is what we wanted, is it not? The orthonormal set M is total in H. Suppose M is not total in H, then we will prove by contradiction. Okay. Now, if M is not total in H, then by the previous result, there will exist a non-zero element X, which will be orthogonal to every element of this. So, by the previous theorem, there is a non-zero element, non-zero X, which is orthogonal to M in H, which is orthogonal to every element of M, by because it is not a problem. Okay. Now, since x is orthogonal in this, therefore, the inner product of this will be 0 for all k. Since x is orthogonal to m and ekh, these are the orthonormal sequences, is it not? Therefore, ekh we are taking to be the what? Orthonormal sequence in m, is it not? And ekh are orthonormal, so be it in 3. Okay. Ekh are orthonormal sequence. So, in this result, let it be this will be B. Okay. And Ek as given is orthonormal. So, we get in is a okay. So, x is orthonormal. So, hence, inner product of x Ek will be 0, okay, for each k, for each k. So, from B, so in B the left hand side is 0, each term will be 0, okay, but the right hand side is non-zero. But what is the right hand side? Right hand side is non x square different from 0, because x is non-zero vector. So, its norm cannot be 0. So, this is 0, this is non-zero, a contradiction is this. Therefore, a contradiction is because of our wrong assumption, then M is not total in H. Okay? So, a contradiction will help you. Okay? So, a contradiction proves that okay, we proves that Parseval relation holds, that B holds. Okay, is it clear or not? For all x, then M must be total. That that if B holds for every x, if B holds for every x in H, then M must be total in H. Total in H. So, this is simple. Now, conversely, what we are assuming is, suppose M is total in H, then Parseval relation must hold good. Okay? So, conversely, assume M to be total in H. Total in H. Okay? Now, again there is a one result which we have not done it, but we will do it here. So, let us, we will first write, suppose consider any x, consider any x belonging to H, okay, and its non-zero Fourier coefficient, and its non-zero Fourier coefficients xe1, xe2 and so on. Okay, Fourier coefficient arranged in the order. Now, define y as the sum of this inner product x ek over k. Okay, not infinite. Okay. Now, convergence of this four thing. Now, this series converges why? Huh? Why did it converges? Because our this result, because our result is a series of this form will converge if and only if this series converges, sigma alpha k square, because the series sigma x ek ek, this series converges in the norm of H if and only if the series of this term converges. Okay, this term converges. Clear? Now it is already given that this series partial, this is convergent, is it not? Norm x square we wanted to prove by Bessel's inequality, sigma of this is less than or equal to norm x square. So this series is convergent. Okay, therefore this will converge. So this will give in convergence is okay. Now if I consider x minus by, okay, now consider x minus by, x is in H, by I am choosing this, and we claim, consider x minus by, right? Now we claim that this vector x minus by is orthogonal to M. Okay, why? Because M E1 E2 N are an element of this. So because the inner product of x minus by Ej, any arbitrary Ej, this is equal to what? X Ej minus by Ej. What is by is this series? E1 E2 N, they are the pairwise, they are orthogonal set, orthonormal set basically. So inner product Ek Ej will be 0 when j is different from k, otherwise 1. So basically you get only one term, that is x Ej, and this will come out to be 0. Is it okay or not? X Ej minus x Ej, and that comes. So x minus by is orthogonal to j for every j. Therefore x minus by will be perpendicular to M. So this is what we have. Okay. Now for contained we have, therefore let V and for every V which is in M, not contained in 4, not contained in this not contained in this form, not contained in by which is equal to k, means not contained in these elements. We can say not contained, we have inner product of x comma v is 0. Why?
We have proved that in the just last statement
that
the y minus
this is okay. This x minus y is 0, and everywhere contained in this is 0, x b will be 0.
the x minus y and Ej are they are perpendicular.
Then
So on that,
what is our x is in H total, okay, and now M is a sequence of orthonormal sets. So any element we can put it in the form of E1 E2 N, therefore we can give it. The coefficient may be different. Why it is? If the coefficient is not x ek, if the coefficient is something different, say alpha k ek, still the inner product x will be 0, is it not? Because that can be expressed in the alpha k ej, and then particular will x we get 0. Okay, so this will be 0 for this. Therefore x minus y, so in x minus by comma v, this is equal to x v minus by comma b. Okay, and this will be 0 again. Is it okay or not? This is also 0, this also, and finally be 0. So x minus by is orthogonal to M. Therefore x minus by is an element of the orthogonal complement, and there is a one proof which I have given. If M is total orthonormal set, then x belongs to M perpendicular implies x is equal to 0. But M is total orthonormal set, is it not? So x minus y will be a 0. Therefore we get x equal to y. Okay. Now once you take x equal to y, then the normality using 4 and there, x equal to y here, okay, then what will be the norm of this? So, norm of x square will be inner product of x x, and inner product of x means sigma k x e k comma sigma j x e j e j, is it not? And that will be equal to, by completion, this is equal to sigma x e k into x e k conjugate, rest will be 0, and that is equal to sigma mod x e k whole square, and that is equal to norm x. So, Parseval relation holds. Okay, is it clear now? Now, x equal to y. So, we can write the y is this one only, means x we can write in this form of this. So, no, basically this start to write x in terms of that we have proved this result, and this proves the result. So, this is okay. Okay. Now, come to now, if H be a Hilbert space, then such space counted dense in okay. Then we have some results for the separable Hilbert spaces. Okay. This, so, what is this result is? Thorough separable Hilbert spaces. Okay. Let H be a Hilbert space. Hilbert space. Then, if H H is separable, then every orthonormal set in H is separable. Okay. And B part is, if H contains an orthonormal sequence which is total in H, then H is separable. Proof. So, part A first. H if H is separable, then every orthonormal set in H is separable. So, let us assume H is separable. Okay. So, it must contain a countable subset which is dense in H. So, by and suppose B is any dense sets in H and M any orthonormal set. Any orthonormal set. Okay. Okay. This is our M. Okay. Now, M is an orthonormal set. So, suppose X is an element of M, Y is an element of this. So, let X and Y with the two elements of M. Okay. Now, if we take a distance of this, okay, the norm of x minus y whole square, if we find, then this is equal to inner product x minus y, and if we calculate this, then it comes out to the inner product of x x plus inner product y y, because x y will be 0, inner product will be 0. Now, x x distance plus y y is two distinct element of this, distance under root 2. Okay. Now this will be 1, norm of x is by, because x is an orthonormal sequence. So norm of x square is 1, norm of x, so this is equal to 2. It means the distance between these two is under root 2. Distance between this is under root 2. Okay. Now let us draw the neighborhood around the point x, around the point y, with a radius root 2 by 3, and here also this is root 2 by 3. It means this distance you are dividing into 3 parts. So this is one part, this is 2 part, this is another. So they are disjoints. This is nx and this is ny. Okay. So now you have got the 2 element of x and a neighborhood which are disjoint. Now B is dense in H. So each neighborhood will have a element of B. Okay. Clear. Now nx and ny, since okay, B is dense in H, since B is dense in H, so there is a V belonging to capital B in Nx and C and a B bar belonging to V in N by such that B is different from B bar. One element B is here, another element B bar will be here of B. Okay. Clear? Now this. Now since this intersection is empty, this intersection is empty. Since M bar uncountable, now what we want to show is that H is separable. Okay. We want it H to be separate. So it must have a countable subset which is dense in this. So we are assuming by contradiction. Suppose it is not separable. It means if set M, orthonormal set M, okay, is a uncountable set. Okay. So if M is our uncountable, then we can find out the countable points. We are in the neighborhood of this as well as in the neighborhood of this. Okay. So since hence if M bar, hence if M were uncountable set, if M were uncountable set, then we would have countably many, we would have countably many such pairwise disjoint spherical neighborhood Nx and Ny type respectively, is it not, for each. Okay. And each will have the elements of B, hence B is uncountable, is it not, uncountable. So hence B will be uncountable, but because B is dense, so that means H cannot be a countable, so H cannot be separable. So what we conclude is, therefore contradiction implies M is countable. That is what we wanted to show. Let H be Hilbert square, then H is separable, then every orthonormal set is separable. M is orthonormal set, so it must have a countable and dense. Clear? The total orthonormal set. Clear? So if we have assumed that is uncountable, so it gives the contradiction H is becomes not separable. So it means M must be a countable set. That's proof. Okay. Second proof we will see next time. Okay. Thank you. Okay. I think this completed. Huh? Only one